So welcome Antonio Jiménez-Pastor. He will talk about DD-finite functions.
Thank you very much, and thank you for letting me giving this talk in the MCA. So today I'm going to talk about DD-finite functions, which is a set of functions that are an extension of the so-called holonomic or D-finite functions. So let's dive into the topic. Let's see what is D-finite function and the holonomic world. But first of all, let's just fix some notation. I will use K, a computable field that is contained in the complex number. So it's a characteristic 0, and everything is a constant inside this field. Computable here means that everything can be represented on a computer. You can put the elements on the computer, you can compute the addition and product, and also compute the multiplicative inverse. Everything, there is an algorithm for everything, so you can compute in any computer with this field. And then we will consider the ring of formal power series and the usual standard derivation in this ring, defined as follows. Just the derivation comes inside the sum, as this sum is a symbolic symbol somehow. So it just come inside and just compute the derivative of each term, and it's the standard derivation, so nothing fancy here. And as you will see during the talk, everything is focused on the implementation or being able to compute with these functions. So everything that I will present here is implemented on Sage, and you can access the code, the documentation, and even a demo just using the links here that are already posted in the forum, just in case you want to check them out. So what is the main definition? What is a D-finite function or a holonomic function? It's a formal power series that satisfies a linear differential equation with polynomial coefficients. And this structure is enough to be able to represent these functions into a computer, because you only need to store the list of polynomials that are the coefficients of the equations and some initial values for f, and you have just described precisely the function f in a unique fashion. And why this set is interesting? Because there are many functions that satisfy this type of equations. For example, all the exponential functions, trigonometric functions, logarithms, the Bessel functions, no matter the parameter. And you choose here also all hypergeometric functions. All the family of PFQs functions are D-finite, the Airy functions, and also all the generating functions that come from the equivalent in the sequences that are holonomic sequences, like the sequence generated by the Fibonacci numbers, the Catalan numbers, all of those things. And as I was talking about, I am looking into these classes because they can be implemented into the computer. And in fact, for D-finite functions, we can find that all these properties are close in this set. So for example, if you have two D-finite functions, their addition and the product is again D-finite, they satisfy another equation, not the same, of course, or maybe the same, but a priori that's not usually the case. So there is an equation for the sum of the functions, the product of the functions, the derivative of any functions, any integral of the functions, and even more, if you have an algebraic function over the field of rational functions, then this is D-finite, and you have all bounds for the order of the differential equation using information from F, G, and A here. And as I was mentioning, everything is implemented somewhere. And for D-finite functions, that was work that has been done through the last decades. There are several packages like MGFan, a Maple package developed by Frédéric Chisac and Bruno Salvi in France. There is the package holonomic functions developed in Mathematica by Christophe Couchen from here in Linz, and also the package Ore algebra in Sage can work with these objects, D-finite functions, and this Ore algebra was developed by Manuel Powers and other people from here in Linz. But that's not the topic of the talk. The topic is an extension of this class of functions called DD-finite, and in particular, something more general that will be differentially definable functions. So as I was mentioning, we have plenty of examples that are definite, but there are some stuff that is not definite, that there is no differential equation with polynomial coefficients, linear differential equation. And for example, we see here the double exponential, which is quite a straightforward extension of the previous functions, is not definite. Also the tangent, that is just the quotient of two definite functions, is not definite. And we have other examples that are not definite, like the p-Weierstrass function, the gamma function, or the generating function for the partition sequence. And if we look to the definition, the first idea was just, okay, maybe restrict to polynomials is just too much. Let's just put there something that is also computable. And what is the first idea that came to mind is just, let's change the coefficients to be D-finite functions. And then we came to the definition of DD-finite. A formal power series is DD-finite if they satisfy a linear differential equation where the coefficients now are D-finite. Now we see in the bottom that the two examples that I said at the beginning, the double exponential and the tangent, now became D-finite. So they satisfy this type of equations. Namely, with the double exponential, we have this first order differential equation when one of the coefficients is the exponential. And for the tangent, we can find several linear differential equations, but this is one example. For the two, when we have the cosine square that is definite using the closure properties we've seen already, and -2 here that is just a constant. So we see that this class already extends the class of D-finites because we have added more functions, and of course all D-finite functions are D-finite. But when we were looking to these definitions and trying to do the proofs to prove, for example, the closure properties of addition and so on, we realized we don't need this definition. We can put something more general. And in fact, the only thing we need is that the coefficients that we have here are in a nice structure, namely in a differential ring. So we put the bigger definition here is a function is differentially definable over a ring R, a ring that is contained in the formal power series ring here, if they satisfy a linear differential equation with coefficients in this ring R. That's all we need. And we denote this set by this dr. And as we can see, this definition extends directly the definition of D-finite function because D-finite functions are just the D of the polynomials, and DD-finite functions are just the D of the polynomials, which is just the iteration over the D-finite ring. And the key property here, the main idea that make things computable is this characterization theorem that links the world of linear differential equations with linear algebra. And we see here that a function is differentially definable over R. So you have this linear differential equation whose coefficients are in R. If the vector space generated by the function, the derivative, the second derivative, and so on, over the field of fractions of the ring R, it has finite dimension. And this is an equivalent. And of course, once you have a vector space of finite dimension, you can compute a basis and you can start working in that finite vector space. And that's great. And you can do operations. And in fact, you can extend these closure properties that we had before for D-finite functions over the rational functions, which was the field of fractions of the polynomials. We can just have the same closure properties with the same idea of the proof. And now for differentially definable functions over the ring R, no matter which ring this is, inside the ring of formal power series, of course, and the field of fractions F here. And just to give a glance of how this proof goes, they are always the same. In the case of the addition, we have that the vector space generated by this addition and all the derivatives is equal to just applying the property of the sum of the derivation. You have this, and you can see that this vector space over here is inside the sum of these two vector spaces. The one generated by F and derivatives and the one generated by G and derivatives. And by hypothesis, in these two functions were in the R, then these vector spaces have finite dimension, the sum has finite dimension, so something inside that finite dimensional vector space has finite dimension too, and everything is done. So it's quite straightforward to prove the closure properties. Now implement the closure properties on the computer is just using these properties over and over again. So at this point, we were just working with DD-finite functions. We were very happy, but since we had this definition of differential dependent functions over a ring R, we realized, okay, with these closure properties, we have addition, we have product, we have derivation, we have a ring again. So we can do the same thing we did for D-finite and build a DD-finite, and we can just keep iterating this process over and over again. And that's where the concept of D-finite functions came into place. As I was mentioning, you have that if R is a differential ring here, then the dr is a differential ring. So we can just keep going and going and going. And the D-finite functions are just the nth iteration of this process, and we have this interesting chain of rings inside the formal power series. We start with polynomials, then we go to D-finite, then we go to DD-finite, and so on, so DM-finite, and keep going, keep going. And the good thing here, once we start looking to this chain, is things start to fit together because we have more properties now. And in fact, we have one property that was not in the D-finite case, that is the composition. Now, if you take a DM finite function, so something in the nth iteration and something in the mth iteration, then the composition, if it's a power series, it's a dm plus m finite function. So it's in the m plus mth iteration of this process. And in fact, we have a bound for the order of the differential equation that this guy will satisfy. And for example, if you have an algebraic function over the dm finite functions, you have something similar as we had in the original property for being algebraic, that the composition is the m plus m. One would say, yeah, but maybe this last row is not so important because if A was algebraic over dm, using closure properties, we had already that A was in dm plus 1, and then using the first row of this, we have that the composition is the m plus 1, and maybe that's enough. You don't need to think more, but it's interesting to try to reduce this number because all algorithms will be recursive on this value. So the smaller the range, the smaller the place you can embed a function, the faster computations will be for this type of function. So having this result over here, even if you increase the order of the differential equation, is very useful in practice. And yeah, once we have this chain, we start looking to some structural results over here. And we saw, for example, that, yeah, from polynomials, we extended to D-finite functions and we add something. For example, we had the exponential was not a polynomial. So in this step, we added something. At the beginning of the talk, we saw that the double exponential was not defined. So in this step, we added something. Is this a general rule? It's true that we always add something here, or this is stabilized at some point. And the answer is this does not stabilize. So you always add something new. And the idea is just extend this exponential idea, right? So we start with E0 is the constant one, and then we define the next iterative exponential as the exponential of this integral over here. And you can see here, the first exponential will be e to the x, then the second iterative exponential will be e to the x minus 1, and so on. Okay, it's just this procedure over here. And we can prove using differential Galois theory that the n plus 1 iterative exponential is the n plus 1 finite. That's quite straightforward using this formula over here, and it's induction argument. But it's not dm finite. So it's there is no differential equation with coefficients in dm minus 1 that is satisfied by this iterative exponential. So as we see, this construction always adds something new. So then the following question is, does this stop somewhere? So we always increase, so we get everything we can get. And the answer is no. I mean, you are in the formal power series. They are really weird formal power series. So this has to stop somewhere. And the question is where? Well, to answer this question, we start looking to differential algebraic functions. So I need to include this definition over here. We say that a formal power series is differential algebraic over R, a ring R, if there is a polynomial, a multivariate polynomial P with coefficients in R with some variables such that P evaluated in F and F prime and so on, and all the derivative of F is 0. So you can say there is a differential polynomial that is that annihilates F, or depending on your background, but yeah, you have this polynomial that annihilates F and all the derivatives. And let us denote by dA of R the set of all differential algebraic functions over this R. We can see here that we are just adding more type of equations, because for differentially definable functions, we were considering only linear differential equations. And now with differential algebraic, we add polynomial differential equations. So it's very easy to see, for example, that differentially definable functions are included in differential algebraic. And also it's quite straightforward that if a ring R is a subring of S, then the differential algebraic functions over R are including the differential algebraic function of over S. And also a classical result here, and also it's true for algebraic functions, if I remember correctly. Differential algebraic functions over polynomials are differential algebraic functions over the constants, which is pretty nice. So you can kind of keep reducing here. And this is the main result of this area is if you have a differential ring, it's true that the differential algebraic functions over the differentially definable functions over the ring R is just differentially algebraic functions over R. And this proof that it's constructive, you can get the non-linear equation from the linear equation of these guys, of the coefficients of this polynomial. And in fact, this is a consequence of this result is that every DD-finite function is differential algebraic. So we are constructing a chain of rings that keeps increasing inside the differential algebraic functions. And then the natural question again is, are these functions all the differential algebraic functions, or is the place where this stops and you cannot get further? But first of all, as I mentioned here, the result here is constructive, and it's implemented on the code that it's included in the package. And for example, for the double exponential, you start with this linear differential equation, and you build this non-linear equation just using the properties of the exponential here. And for example, for the tangent, just using this differential equation and the properties of the cosine square, then you build this non-linear equation. Of course, this constructive argument does not provide the minimal equation. For doing that, you probably will need to take into consideration the initial values of the tangent, but here we are only using the differential equation, and that's all we got. But here we get the linear differential equation of order 5 and degree 4 with constant coefficients, which is okay for us. As I was proposing before, is the inclusion true? So we have that the D-infinity set, so the union of all this chain, is included in differential algebraic functions. Is true the other way around. Well, for some examples, we start looking at them, and it's true you can find an n when everything works. So for example, if you consider the Riccati differential equation, which is this nonlinear equation, y prime equals a polynomial of degree 2 in y, and you said that the functions a, b, and c are insuitable steps of the chain. So for example, a and b are D-infinite, c is Dn-1 finite. Then you can prove quite using the usual chain of variables of the Riccati differential equation that the solution is Dn+2 finite. Okay, you have one way to go, but unfortunately, there are some cases that this inclusion is not true, so you cannot transform back. And for example, a result from Norman Toppa van der Put, if you consider the solutions to this nonlinear equation, y prime equals y cubed minus y squared, which is quite simple, nothing fancy, then there is no n where this solution is in D-infinite. So you have to look. You have maybe to look to another ring of coefficients that is not polynomials. You may want to start with another thing, but you cannot have this inclusion for all. So this is not true. This is not equal. This is different, and this is smaller. This D-infinity is smaller. Okay, but to summarize what I have said here is we started with D-finite functions. We have extended it to a more general framework, which is this DD-finite, D3-finite, Dn-finite, and so on. And everything is implemented already in Sage. You can work with it. And we have to see how this chain of rings are related with the differential algebraic functions and what are the differences between them. And for the future work, we will need to, we are working on how to compute fast truncation of these D-infinite functions. It can be helpful, for example, for numerical evaluations of the function, which is the second bullet point here. Also, we are working on how these sequences, so we look to the formal power series, we look to the sequence of coefficients. This may have combinatorial meaning as it was the case for D-finite functions. And also another point of work will be multivariate DD-finite functions. And since we have 5 minutes left, let me show you a teaser of the code, which is not the demo, but it's a small demo of the whole package. So this is a notebook in Sage, and directly after loading the package, I hope you are seeing the notebook. Otherwise, please let me know. Once you load the package, you have already the rings defined of D-finite and DD-finite functions. You can just see here that this returns what you expect. The differentially definable functions over polynomials, the differentially definable functions over the D-finite ring. And you can start building objects here right away, no problem. Like you use the ring dot element and you put the list of coefficients and you put the list of initial values, and it builds you the object that is the function that satisfies the linear equation that you were looking for and has some initial values. And as, there are plenty of building examples, and here you see the documentation and a list of functions. You have all the trigonometric functions in the package, all the arcsine, arctangent, everything, the exponential function, the logarithm, the Bessel and Struble functions are also included. Some families of orthogonal polynomials are included in the package already, so you can just use these methods to create these objects within the package. You don't need to know the differential equation. Also, as I mentioned, the hypergeometric functions and the PFQ functions are also included, the solutions to the Riccati differential equation, Mathieu functions, and so on. So there are plenty of examples here already included, and you can start working with it. For example, you can compute an equation that is satisfied by the cosine of the exponential -1 square, and it's just this would be D-definite because exponential is definite and cosine is definite. And you see here the equation is just an order 3 differential equation with a G1 in the first derivative coefficient that is defined with another linear differential equation, this time with constant coefficients and some initial values over here. And you can do the same, for example, with the sine of x of the exponential -1 square, and you get another differential equation very related since sines and cosine are really close, but different initial conditions, as you may see here. So here the initial conditions were 1, 0, -2, -6, so on. And here is 0, 0, 2, 6, and so on. And you can just check with these objects. You can type everything you want in Python. And for example, you can check identities like, is the sine of exponential -1 square plus cosine of exponential -1 square equals to 1? And answer is, of course, yes, because that's exactly the trigonometric equality that we all know. And that's all you need. You just type it, check it out, and oh, it's true. Okay, perfect. And as I was mentioning, you can just compute truncations of these objects. You can get, for example, the 1000th element of the formal power series of the tangent, and you see here the value. It takes just 6 seconds, and it's just a very large number, but it is what it is. It's a rational number that is this big. I am afraid I cannot do much more than that. So I think with that, I will thank you and conclude my talk here.
Thank you.
Thank you. All right, so we have time for questions. So questions.
I have a question.
Oh, go ahead, Greg.
Oh, sorry. Okay. I'm wondering. So since all these D-infinite functions and then the D-infinity ones happen to be differential algebraic, is there any way to obtain a bound, say on the order and degree of the minimal algebraic differential equation satisfied by some D-infinite function? Of course, with more information. Maybe I look at the order of the coefficients or something like this, the order of the differential equation over dn-1. But is there some kind of way to try to go back?
You can do something, but it's very vague and it's not very good bound for sure. Because as I was mentioning, this result here is constructive. You know exactly what it is, and this is just a determinant. And you have bounds for the order and degree of those elements in the determinants, and you can bound that. but and then the minimal will be smaller for sure, but at least in the order of the nonlinear equation. So you can do something, but the bound is not good. For example, with the tangent, the minimal equation has order 1 and degree 2, and here we have order 5, degree 4. Okay, yeah, these are bounds, but but not good bounds, right?
And could you extract the minimal one in some way from this other one?
That's something I don't know. That's something I would like to take a look into, but currently I don't know how to get the minimal. I'm pretty sure that, for example, for the tangent, the minimal equation for the tangent, the solutions does not form a vector space, right? And this procedure that we are doing is any solution to this equation will be a solution to this equation. So you need at least to have some vector space inside, and you need to use the initial condition somehow, but that's something I don't know how to use properly yet.
Yes. Thank you.
More questions?
Yeah, so I have a question. So thank you for the very nice talk, and thank you for making the My Binder notebook, because I had a lot of fun playing around with that yesterday. So in combinatorics, one of the most useful things for array algebra and these kinds of packages is the ability to guess an operator from an initial sequence, initial terms of the sequence. So do you have any capability for extending the guessing from D-finite?
For now, no. I tried to, but it's very, very slow to do a guessing that you may have instead of D-finite, C-finite coefficients. That's a reduction of the thing, but so far I don't have a good way to do guessing, and I'm not sure how to properly do it. But that's something also I would like to take a look after this is implemented, just jump into the guessing, but sounds quite tougher than the D-finite case.
Yeah. Okay, thank you.
Welcome.
More questions?
So
I have another question, maybe.
Please go on.
First of all, I forgot to say, like Stephen, thank you for the very nice talk. Should have started with that.
Thanks.
I'm also wondering in combinatorics, often one consequence of showing that a certain Jenny series is definite is that you get asymptotics on the growth of the coefficients. I'm wondering if you have something kind of immediate from knowing that something is D-finite. Can you come up with reasonable detailed asymptotics on the growth of the coefficients?
We are working on that right now. It's part of the work of studying these truncations of the functions that I mentioned here. And the thing is, immediately you can see kind of a bound, because for D-finite, they cannot grow more than something exponential because there is no space for it. If you are DD-finite, you cannot grow more than double exponential, and that's the easiest result you can get. But to describe a precise asymptotic from one equation, that's work in progress.
Okay, more questions? Or we have a half an hour for further questions if you wish. We can maybe now move to the next talk, right? Thank you.
Okay. Thanks.
Thank you.
Yeah.